Hello, I wanted to go over Pop Quiz 5 and give you an opportunity to see all the problems worked out in detail. So the three possible rate laws in the quiz are shown here. I encourage you to pause the video and determine the overall rate law and compare to the work here. So the first thing we're going to do is write the rate law for the slow step. So it's D times A. We look at the role each play, and D is an intermediate because it is made first and then consumed. Because it's intermediate, it is not an acceptable rate law. So we determine KC from step 1, solve for the intermediate so that we can substitute it into our preliminary rate law. And if we do that, we see we have 2 A's and 1 C, which gives us A squared times C, or second order in A. In the middle set, we do the same thing. The rate is the slow step, D times B now. The intermediate is still there. B is playing the role of a reactant. We have to determine Kc again. And if we do that, we get the same expression for the concentration of D. We substitute, and we see that we get the rate law of ABC. Now A is first order in. The reaction is first order in A. We can do that for the last set, which is fairly straightforward because the first step is slow, so we can write the rate law directly, B times C. And that's zero order in A. Okay, so these are the three analyses that were possible, and then we were supposed to match them to data. So zero order in A, remember if A is not in the rate law, but it's an overall reactant, it is zero order. Okay, so here we have these two data sets. And the question is it first order, is it second order, or is it zero order? Okay, so we're going to go through an analysis. We do it several times in the video. I really encourage you to practice, pause, practice zero order, pause, watch, compare notes, try first order, compare the notes, try second order, compare the notes. Okay, so here's zero order. Zero order, we're looking at the linear relationship of concentration versus time. So we're asking, is the slope of concentration versus time the same at the beginning of the data set and at the end? Okay, and if we do that, we quickly find out that no, it is not zero order because when we calculate the slopes, they are not the same in the data set. If we do it for, remember that was for concentration versus time. If we do the first order analysis, that's asking is the ln of the concentration, this is the natural logarithm of concentration slope, is this constant over time? We take the first 2 points and the last 2 points. And when we look at the concentration, the slope at the beginning and at the end, we say no, it's not first order. Sorry. Well, so it's not zero order. We just checked that. So I'm bringing it back. Sorry, I pushed the wrong button. Okay, not first order, not zero order. And now we go to first order. And if we go to first order, we see that it is not first order because the ln's were not the same. Okay, this takes us to where we were. And now, if we don't have zero order at first, we evaluate second order by taking the reciprocal, right? So we want to know, is this slope the same at the beginning, at the end, the reciprocal slopes? And when we do that, we see that yes, both data sets, remember, each of these slopes are either minus k for zero in first order or positive k for the second order. And when we look at that, we see, yes, the slope is the same for the reciprocal in data set 1. So data set 1 is second order in A. So that answers one part of the mechanism. We see that data set 1 is second order. We do the same analysis for data set 2. Is it zero order? Is it linear with concentration versus time? And we see quickly it is not zero order. We do this first order analysis. Is the ln with concentration the same for both sides? And we take the ln of both sides and compare. Sorry, I ran out of room there. We see that yes, the slope is the same. And so the data set 2 is first order. So data set 2 is first order. Data set 1 is second order in A. Okay. So how does that help us? That helps us because when we go to the mechanisms now, we can assign second order behavior in A is data set 2. First order behavior is data set 1. So when we come back to our 3 possibilities, summarize here, this was second order in A, that would be data set 1. This mechanism was first order in A, that would be data set 2, not 1, data set 2. And the rate here, KB times C, is neither data set 1 nor data set 2. Data set 2 for the middle one, first order. Okay. The next question was a fast slow mechanism. So we did some elements of that in the first step. So we always write the rate law as the slow step. That's always the first thing we do. We evaluate the roles of each of the species in the rate law. C is an intermediate. A is an overall reactant. So we write out Kc from step 1. That gives us a way to substitute for C. So C is Kc A B squared. Keep in mind that we don't really use the equilibrium constant Kc for anything. It just becomes a new constant. So when we substitute for C, we now get the rate as K times A times B squared times the original A from the rate law, which gives us K A squared B squared. So we can analyze this under second order A or second order B, keeping the other constant. Okay, here you're given a data set of barbituric acid at room temperature, and we want to know the half-life of the reaction. It starts off at 3 times 10 to the minus 4, so we want to know at what time is it going to 1.5 times 10 to the minus 4. So first we need to know what order. So we check zero order. That seems reasonable to start. We want to know, is the data linear? We check the first 2 points, the last 2 points, and we see that the reaction is not zero order. So we check first order. That would be the ln of the concentration. We take the difference in the ln of the concentrations of the first 2 points, subtract them from the ln, or we're saying set this equal to, is it the difference of the ln of the last 2 concentration points the same? And what we see is, yes, it is first order with a rate constant, right? The slope was minus 0.092, but the K value is positive 0.092. That allows us to find the half-life if we use the formula. ln of 2 is 0.693 divided by K, and we get 7.5 hours, which is exactly where we'd expect it to be, between 5 and 10 minutes, or hours. If we go the other route where we don't use the formula and we just say, okay, we know the initial concentration, we want to know how much time it takes to get to half of it. So we take 3 times 10 to the minus 4 divided by 2, get 1.5 times 10 to the minus 4. Now we can solve for time using the integrated rate law. Solve for time. Since we know now all three of these values, we plug in the ln of 1.5 times 10 to the minus 3. That's the concentration at half its value. The original concentration, 3 times 10 to the minus 3, divided by 0.092 minus 0.092, and we get 7.5 hours. So in both cases, whether you use the formula or whether you use the integrated rate law, you obtain the same value. This was the second data set. So the preliminary analysis is to find the order. We want to know, is this zero order or not? So we check linearity, the first 2 points and the last 2 points, and we see that no, the data is not zero order. It is, they do not have the same slope at the beginning of the data set and at the end with concentration and time. So we go to first order, we check, is the ln linear with time? So we do that, we find the slope at the beginning, the slope at the end. Compare them, and the answer is yes. Get the exact same value, minus 2.5 times 10 to the minus 3, which is equal to minus k. Now with this information that we have first order kinetics, we can then use the formula again, ln of 2 divided by k, and we get 275 minutes, which is between 200 and 300 minutes, which is what we'd expect in the problem. Right in between these two values, so where 0.05 would be. We could also calculate it using the integrated rate law. 0.1 is the original concentration, half of it is 0.05. We can solve for it this way, and we get the same answer, it's just not using the formula. But you can always use either expression. Alright, so we have a new data set, and we want to know how much time it takes to get to 1 times 10 to the minus 3. So, zero order analysis asks, is this linear with concentration? And the answer is no. It is not the same slope. We do first order analysis, is the ln linear? And we see that by doing this calculation that the answer is no, it is not the same. So what we have is a second order analysis. We can verify it and calculate k by doing the reciprocal analysis, is what we're doing here. And when we do that, we see that yes, k was 0.72. So we have second order analysis, we have k, and now we can answer the question. The question is, how much time does it take to get to 1 times 10 to the minus 3? So by using the rate law, what we do is we say, okay, 1 over lithium H4 is 1 over its initial concentration plus k times T. The 1 over 0.1 is coming from the initial concentration. Alright, so if we solve for time, we get 1 over the initial concentration of the lithium aluminum hydride minus 1 over the initial concentration, 1 over 0.1, and we divide by k. If we do that, we obtain 3640 minutes. Now there are a couple other versions here. Some students receive 3 times 10 to the minus 3, and we just plug it in the same formula, and there we get 1188 minutes. And then the last one, which is 6.8 times 10 to the minus 4. How much time does that take? And we get 5:53:70 minutes. So once you find the order, you can use the linear, use the integrated rate law to determine the time it takes for a certain concentration to be obtained. Right, the final question was asking about the factor that the rate changes at different temperatures. All right, so the K, so keep in mind we have to convert to Kelvin, and what we see by the data is that the factor that the reaction increases, going from 673 to 473, was about 3,170 times. So 3,170 times faster. Okay, now that we know that, we can plug it into our equation. The activation energy is minus R, minus 8.314, times the ln of the factor divided by the difference of our reciprocal temperatures. If we do that, we get 108 kilojoules per mole. We can do the other two very similarly. We put the K at 573 divided by K at 373. So we put these numbers in and we see that the reaction is 193 times faster, these two different temperatures. So the activation energy is minus R, minus 8.314, times ln of the factor divided by the reciprocal temperatures in this problem, 573 and 373. If we do that, we get 47 kilojoules. The final problem is, we see that 500, so we have 773, the reaction rate is 5.7 times 10 to the 6th, or third, and then at 573 kelvins, 2 times 10 to the 2, which is a factor of 20. We see that the activation energy is minus 8.314 times the ln of 20 divided by the difference in reciprocal temperatures, and that gives us 55 kilojoules. Okay, so these are all the questions from Pop Quiz 5 worked out. Really encourage you to go through these problems and make sure you can do them in a reasonable amount of time and that you have notes associated with them. They will be very similar to problems on your exam.